Okay, let's move into the worksheet number 9 from lecture number 9. So now if I remind you what we have done in lecture number 7 and 8, lecture number 7, we were talking about the charge particle moving inside magnetic field or the current carrying wire inside magnetic field, how they will create a magnetic force on those charge particle or current carrying wires, right? And then lecture number 8, we discussed that by using the current, we will be able to create magnetic field. So creation of magnetic fields, we discuss in worksheet or lecture number 8. So now here, the Faraday was the scientist that think about, like after many years, they try to think about if I can create the magnetic field from the current, can we do the opposite? What is the opposite means? Opposite means, can you create a current by using magnetic field, right? That is, we call it as induced EMF. Because of induced EMF, it will create an induced current. That is the Faraday's law. So Faraday's have done series of experiments, and I explained those experiments in the lecture part. Make sure that you watch it. And those experiments show you how the induced EMF will be calculated and also how the direction especially will work in these experiments, right? So now Faraday and Lenz are the laws that we are working in here. Faraday's law, right? So what the Faraday is saying that he's saying electric flux. You remember that we talked about the electric flux by using electric field and the cross-sectional area. Similar to that, we should have something changing with the time here. That is the magnetic flux. So magnetic flux. So we use the symbol phi B for that, magnetic flux. So magnetic flux means basically how many magnetic field line pass through the cross-sectional area of the object that you are taking, right? So now this magnetic flux will be able to write by using B and A and the cosine of theta. So cosine of theta will be in between the angles of B and A vector. Now B is the magnetic field, A is the cross-sectional area of the loop that you are using, right? So then angle between these two is theta. What that means is if the magnetic field is aligned with the cross-sectional area, that means the theta equals 0, at that time, you're going to get the maximum magnetic flux. So when the theta equal 90 degrees, you know that cosine 90 is 0, then magnetic flux will be 0, right? So that's what the magnetic flux is, right? So now it's very important that you understand what is the cross-sectional area means, because if you have a loop, your cross-sectional area is a vector. Its vector is pointing outward of this page or inward of this page. That's the direction of the cross-section, right? That's, you really need to understand what is the vector cross-section represent to you. So that's the cross-sectional area. Area is this in magnitude, but direction can be pointing out or in from your notebook or your screen. So that's the direction of the A, right? So now let's talk Faraday's law a little bit. So I know that I discussed about the series of experiments that Faraday experienced or observed to understand this feature. So that's where the Faraday's law developed, because of by watching that experiments, by watching what is happening and what is changing and what happened. Then he realized that something is changing with time. That is, he defined it as magnetic flux. If you are able to take the rate of change of that magnetic flux, that means with the time magnetic flux change, he call it as, with the negative sign, he call it as EMF, that is the induced EMF. induced EMF means basically voltage. Because of that, it will create the current that we call it as induced current, right? There are a lot of application on the Faraday's law, transformers we discuss, and also induction coils that we have, induction ovens we have. These all are Faraday's law, and also eddy current, and those things can be explained by using the informations that we have, the conceptual information from the Faraday's law. Okay, so now you know that the phi b is b and a and cosine theta. Now you can see this EMF can be induced by change in magnetic flux. That means one way you can change is change of magnetic field, magnetic the cross-sectional area, and the angle between these three. So you have three change in variables. Those are the three change in variables that you can change the induced EMF on the circuit, right? So now this negative sign, as we know, it's coming from the lens. So this sign is coming from the lens law. So that define you the direction of the induced EMF. What the lens realized that after you create the EMF, that EMF will create by your object to oppose the change of magnetic flux. So this will say oppose the change of magnetic flux. That's what the lens law represent to you, right? So now, especially in this worksheet, I'm planning to experience how to get this negative sign, how to do it for the some conceptual questions, and how we're going to apply this into the motional EMFs especially. So motional EMFs. Motional EMF means you can have a conducting wire. If I have this wire, since I have resistor here, this is my conducting piece of the wire that I can move this way, I can move this way. Now this will create, if I keep this inside magnetic field, this will create the current in the loop, clockwise or counterclockwise, depend on that our right-hand rule that we can use. And also we can use the Lenz law to find it out the direction, and that will create the induced EMF. According to that, this loop will create the current clockwise or counterclockwise. Then that EMF you will be able to calculate, and you will be able to calculate net voltage of the circuit and net current of the circuit by using Ohm's law, and those things we can combine electricity and magnetism together in here. Okay. So now induce the motional EMF means basically you see that you're going to change your area, you can change magnetic flux, you can change the cross-sectional area, the cross-sectional area or the theta angle according to this formula. According to that, we need to develop what you're going to change, add that into the formula, and then find the rate of change of that quantity, and then you're going to calculate the induced EMF, and hence we can calculate the current. Okay, so that will be the parts that we are going to do it in here. So now first question, actually I'm doing some conceptual understanding to understand the direction, that means Lenz direction of the Faraday's equation. So now first one, if a north pole moves toward the loop from the above the page, in what direction is the induced current is? Okay, so now north pole moves toward the loop from the above on the page, right? So now your page is a screen. If you have it on your notebook, it will be on the desk, right? So I have the page loop like this. It is staying on the page. So now you're going to move the north pole towards the loop above the page. That means I'm going to bring it in my side to the screen. That means my north pole, I'm going to bring it from the top to the page, right? So now it's asking, when you bring this north pole, it will create the current on the loop on the screen, that loop has the current and current direction determined by the lens law. So now we need to think what is happening, right? So as we know, epsilon will be negative change of rate of flux. So now change of rate of flux, if by bringing the north pole towards the coil, if you increase the change of flux, you need to decrease it. That's the negative sign means, right? So now we see what will happen in here. So you keep the north pole at rest. There is no current on the loop. Now you're going to bring the north pole towards the coil, north pole towards the coil. That means you create a magnetic field lines into the board, because north is emitting the magnetic field lines to this. Let me draw it in here. What will create is magnetic field lines, try to create inward by bringing the north pole. So now basically you increase in magnetic flux towards the screen, but negative sign saying it will create the current to make it opposite direction. You try to decrease it by creating the current in opposite direction. Now induce one do opposite. That means opposite means outward. To create the outward, then you know that by using your right hand, your thumb to the point into the coil, and your inside of the coil is outward magnetic field, your second right hand, then your current direction should be counterclockwise direction. And that's the part that I am asking in here. Okay. Still take little time. It's okay, but try to understand it. I will explain one more time. So you bring the north towards the coil. When you bring the north towards the coil, you create the magnetic field into the board. Then negative sign represent that it will create the magnetic field opposite direction to reduce the magnetic flux. To opposite direction creation will create the current counterclockwise direction. And since I am not changing the area, not changing the angle, only thing I am changing in this phi right now is B, because I am not changing any of those things on this example. I'm only changing the B, right? I increase the B, I need to decrease the B. Decrease B, I need to create in opposite direction B. Okay, so that's how you realize it. Okay, so now let's move into the second question. If the north pole moves towards the loop in the plane of the page, what does induced current, what is the direction of the induced current, right? So now you see that north pole moves toward the loop, the plane of the page, right? Plane of the page means you have loop like this, but north pole moves toward the loop in the plane of the page. That means you're going to move the north pole like this on the same page, not on the top, not on the bottom, right? You bring the north pole towards the loop on the same plane, right? So now when you do it, you know what will happen. What will happen? This will create the magnetic field lines in this direction, right? So now here it's very important what happening when the magnetic field lines are perpendicular to the cross section. Cross section of this one is outward or inward. They are perpendicular. When they are perpendicular, theta equal 90 degrees, then your magnetic flux going to be 0. That means there is no creation of the magnetic flux at all. Because of that, no induced current. Here is no current. Okay, so now let's move into the next one. A wire loop is being pulled to the right through the uniform inward magnetic field. So you have uniform inward magnetic field, right? So you have loop that you're going to pull to the right, uniform inward magnetic field, you're going to pull it to the right. So you have a loop here, you're going to pull it to the right. So what is the direction of the induced current? Okay, so we'll say we have We are not going outside of the magnetic field. We have uniform magnetic field everywhere. What you're doing is you are pulling the wire, the loop, to the right direction, right? So now you need to understand, do you change magnetic flux? Magnetic flux will be changing by changing B, by changing cross-sectional area, or by changing angle. Do you change any of those in this example? You are not changing anything, right? Everything is as it is. Because of that, no current. Okay. If you are breaking this into the uh, air that don't have the magnetic field, that will be different. Okay, we're going to probably have that question on the bottom. So now let's move into the part D. Now part D, I have a wire loop is being pulled to the right through the uniform inward magnetic field that suddenly ends. So that's suddenly end. What is the direction of the magnetic field? Okay, so now we have exactly the same question as part C, but your magnetic field going to suddenly end. Your loop is here, right? So now what will happen? Now what will happen in this case? So your magnetic field going to be end. That means what you are changing here, you do not change the loop. You do not change the direction. Only thing you are changing is magnetic field. Your magnetic field going to be decreased when you bring it to the right direction. There is no magnetic field on the right. So now magnetic field is decreased, but coil try to create the magnetic field. So what is decreasing? B is decreasing. B is decreasing. What the coil have to do is B, he have to increase it because of negative sign. How to increase it? I need to create the magnetic field inward direction by sending the current through the loop. So now current through the loop, you need to send in this direction. Use your right hand, you will see that inward will be inside the loop. So that's how you create the magnetic field. So that will be clockwise direction. Okay. Okay, now part E. What is the direction of the induced current if the B field suddenly increase inward while the loop is in the region? Okay, so you have magnetic field, right? You have magnetic field. And then what you're going to do, you have a loop. But you're going to increase the magnetic field on the right side. Left side is low magnetic field, right side, I mean weaker and is stronger on the right side. So now it's asking what will be the direction of the current. So now you see, you increase the magnetic field in inward direction. You increase magnetic field in inward direction. What coil have to do is, coil have to reduce it. Coil have to create B to decrease the magnetic field. That means you need to create the magnetic field outward direction. To create in outward direction, what coil have to do is, inside the coil should create the magnetic field outward direction. That means this will carry the current in counterclockwise direction. Okay, let's move into the next term. If the coil is shrinking in a magnetic field pointing into the page, what is the direction of the induced current? You have the let's use the blue color. You have a coil, right, or the loop that has the magnetic field pointing into the page like this. And then what you're going to do is you're going to shrink the coil. Shrinking coil means what you are changing, you're going to shrink it. Shrink it means you are decreasing your A. You are decreasing your A. Now by decreasing, you decrease the magnetic flux. Only thing that I can change is magnetic field. That means I basically decrease in cross-sectional area means decrease in magnetic flux at the same time, right? That means I need to increase what the coil has to do is increase magnetic field on the same direction. If you increase magnetic field in the same direction, the magnetic flux is staying fixed. So now creating magnetic field inward direction, you know that I need to carry the current in clockwise direction. Okay, so number G, wire loop is being pulled away from the current carrying wire. What is the direction of the induced magnetic field? Okay, so you have current carrying wire, I. You have the loop. You're going to bring this to the right, pull away from the current carrying wire. What is the direction of the induced current? What actually will happen? Closer to the wire, you have stronger magnetic field, getting weaker and weaker when you get outside, right? So that means basically your magnetic field is decreasing in inward direction. That means coil have to create the current to increase the magnetic field, need to increase the magnetic field. That means I need to create the same direction magnetic field, but need to increase. To increase it, you need to create the current in clockwise direction. Okay. And my last question, what is the induced current if the wire loops moves in parallel to the current carrying wire? So if you move the loop parallel to the current carrying wire like this, right? So current carrying wire, you move the loop exactly in here. So now you know that we have magnetic field stronger here, weaker here, but by moving this wire up and down, it will not change anything. So nothing will change because of that no current. Okay, so now let's move into section number 2. So now motional EMF, we're going to talk about massless frictionless bar with the length L in red piece on the diagram. 1 meter length is being moved at a constant velocity. We have velocity 10 meters per second, and left to the right, from left to the right to conduct interest by the external force F as on in the figure. If the system is immersed in the uniform magnetic field out to the page, this dot magnetic field is 2 Tesla. And what is the induced current? I have resistor here, R equal 5 ohms. And we need to calculate the induced current and also the direction. Okay. So now let's see how we can go to calculate it. So now we know that Faraday's law is just ignoring negative sign. We're going to get the sign by using the directional informations. We know that delta pi b over delta t. So now you need to simplify this formula because pi b is equal to b and a n cosine of theta. Definitely theta angle is just 0 here. So because of that, cosine theta is 0. Because cosine 0 is 1, sorry. So cosine 0 is 1. Because of that, this part will be 1, right? Because of that, pi b equal b and a. So now you can see that by putting that into here, delta pi b is b and a over delta t. So, but you see that b is uniform. You are not going to change the b. B is uniform, right? Uniform magnetic field. Because of that, I can take the B outside from the delta. Then I have delta A over delta T. That means change of rate of cross-sectional area will be the part that we are doing here. So now it's very important that cross-sectional area that we are working is this area, right? So that area, you still see your L is not changing. Cross-sectional area in here will be L times X. L is the constant, right? Because of that, I will be able to write L also outside. Then I have delta X over delta T. As soon as you know, this is change of rate of displacement, that will be just velocity. So now my final formula to use, epsilon equal B, L, and V. Okay, that's simple, right? So now, since we have all the informations, I know I can calculate the epsilon, but that's not what the question is asking. Question asking induced current. So this is induced EMF. How do you calculate induced current on the loop? So if you go to the electricity part, this will create a voltage with a power supply, and it will go through the 5 ohm resistor. Then you know that epsilon will be equal to minus I times R will be equal to 0 because of that epsilon equal I times R. Then I can replace this I R equal B, L, and V. I need to calculate I. I will be B, L, V over R. So now we have all the informations. We can plug it in here. So B is 2 Tesla. L is, write the L value, 1 meter. 1 meter, and velocity is 10 meters per second divided by 5 ohms. That will give you the value of I for you. So we have 4 amps. Now finding direction. So now this is where that you are thinking about the direction. By moving this red piece to the right side, you are increasing what? You are increasing cross section, right? That is right. By increasing cross section, you are doing flux increase basically, right? So now you need to decrease the flux, right? To decrease the flux, you see that you need to decrease flux. To decrease flux, what can I do? I need to decrease the flux. To decrease the flux, what I can do is I am not able to change the my cross sectional because I increase it already. I cannot do anything for that. It keep constant after I increase, keep increasing, but that will not affect to do the opposite thing. I need to decrease the flux. To decrease the flux, only thing I can do is now change in B. You can change the B, you need to decrease it. That means you need to create magnetic flux into the board, right? To create the magnetic flux into the board, which direction this wire can carry the current? Okay, so now you need to think. I'm going to erase this little bit because I have a lot of things drawn in there. Okay. So now we have this one. So I need to increase the magnetic flux on the loop. This is the loop in this direction. I need to create the magnetic flux outward direction. Now you know that you need to carry the current on this wire this way. That is, we call it as clockwise. So this current is clockwise. That's the direction. Okay, so now let's move into our next question, a little more about the same thing about the motional EMF. Okay, so now in this question, in 100 loops, so we have number of loops. Oh, change the color. N equal 100 loops, and we have L, you see the L distance 5 is given, this length, right? L is 5 centimeters. I'm going to write it by using meters, 0.05 meters. And then resistance of the wire is R, that is 100 ohms, is position perpendicular to the uniform magnetic field. B is outward, the inward direction, 0.600 Tesla. Now this is time dependent thing, right? It is quickly pulled from the peel at constant velocity, moving perpendicular to B to a region where the B drops abruptly to 0, right? At time equals 0, the right edge of the coil is at the edge of the field. After 0.1 second, whole coil reach the field free, right? So now find A. So now, according to this information, you can see that you have a magnetic field at time equal 0, the coil is inside the magnetic field. At time equal that will be your magnetic field 0. So time equal 0.100. At that time, magnetic field, that means coil is basically outside, right? So now let's see what we can do it in here. So formula that we have is epsilon equals, let's do part A. Part A asking find the rate of change of flux. So let's do that first. So answer the question very carefully what it is asking. That's how we can see the understanding. A asks rate of change of flux through the coil. That means I need to find delta T, or I need to find basically epsilon for the coil. So now here we need to do what we're going to change in 5B in here. You see that you change in magnetic field because you had magnetic field B, you're going to change into 0 after 0.1 second. That means you are not changing cross-sectional area, but you are changing magnetic field with the time, right? So now you know that you can write this as A cross-sectional area. I'm going to write it as L to the power 2, right? And then you have delta B over time. Delta B over time is L squared. Your B final is basically you're going to have 0, and difference between that will be B minus 0 divided by time is 0.1 second. So you're going to plug those numbers into here, and then the number I have is 0.015 volt. That is the rate of change of flux through the coil, right? The EMF and the current induced. Now B asking about the EMF. EMF equal, since this is per coil, I have n number of loops. That means I have n times delta pi B over delta T. There is nothing that I can do. I just multiply by 100, right? Because number of loop is 100.15 volt. So that will give me epsilon equal 1.5 volt. Now, induced current. Now I need to, second part of that is calculating induced current. Induced current will be able to calculate by using your information about the resistance, right? So in EMF and current, right? Let's calculate epsilon equal pi times R. So now I know that I can calculate the current by taking epsilon divided by R. So that will be 1.5 divided by R is 100 ohms. That will give me 0.015 amps. Make a little more space in here. Okay, that will be my part B. And now let's move into the part C. Part C asking how much energy is dissipated in the coil. So now energy dissipated, we know that we can calculate by using energy equal, by using the power and the time. Right? Do I know the power? Power, we can write it as I squared R and time. So I have I squared, I have R, I can calculate the energy now. I squared is 0.015 times 100 times time is 0.1. That will give me the answer as 2.25 times 10 to the negative 3 joules as energy. And my last part, D. What was the average force required to pull this? All right. So now the average force you can calculate by using two different methods. One is after you calculate the work done or the energy, we know that we can calculate the work done or energy equal force times distance, right? then I know that I will be able to calculate the force by using energy divided by energy that you calculated divided by the distance it travel, right? So now this will be 2.25 times 10 to the negative 3, going to divide by the distance is just L, right? 0.05. So that give me the force equal 0.045 newtons. That is one way. Another way you can think by using your magnetic force you can calculate, because magnetic force will be the same in this case, right? So magnetic force equal number of loops times I times B times L times sine of theta, that will be just 1. So you can do this calculation, that should give you exactly the same number. Okay, whichever way will be fine. But I think I like to use this one because we are working with the magnetic force right now. Okay. Okay, so now number 4. Okay, let's read it. Square loop of wire length. So we have square loop with the L equal 0.05 meters. Uniform magnetic field is 0.16 Tesla. What is the magnetic flux in the loop? What is the magnetic flux in the loop? Okay. A and B is when B is perpendicular to the face of the loop and when B is angled 30 degrees to the area of the A of the loop. Okay, so now it's simple, right? So A, we're going to calculate the magnetic flux. So magnetic flux will be equal to B times A times cosine of theta. It's asking perpendicular to the face of the loop. That means this will be equal to 0 because cosine of 90 will be 0, right? That means in your part A, flux going to be 0. Now part B, when B is angle of 30 to the area, how do you calculate magnetic flux? Magnetic flux will be again B and A and cosine of theta. So that will be 0.16 Tesla times area L squared. Area is L squared since it is a square. So 5 squared and cosine of 30 degrees. So that will give you magnetic flux 3.5 times 10 to the negative 4. What will be the units of magnetic flux? Webers. Okay, that's simple. Okay, now we're going to move into the number 5. So number 5, the charger of the cell phone contains transformer. We're going to work with the transformer that reduce the 120 AC voltage into 5 voltage and to charge 3.7 battery. AC to charge 3.7 volt battery. It also contains diodes to change 5 volt to the 5 DC. Suppose the secondary coil contain 30 turns and the charger supplies 700 milliamps. So calculate the number of turns on the primary coil. So now we have primary coil and the secondary coil in here. What is given in here? So we have voltage of the primary coil. That is what the 120 is, right? That's the coil that you transform into 5 volt as the secondary coil. Secondary coil we have 5 volt. In addition to that, it says secondary coil contain 30 loops. That means number of loops in the secondary coil is 30 and the charger supplies this much of current. That means secondary coil current is 700 milliamps 10 to the negative 3 amps. Okay, so now part A asking what is the number of turns in the primary coil, right? So now that's simple, right? So if you go to the transformers, you have step-up transformers, step-down transformers, whichever the transformer that you are using can have the ratio of NP to NS ratio will be exactly equal to the ratio of the voltages. So now you just need to find the NP from here. NP is equal Vp over Vs times Ns. So that will be 120 over 5 times 30. Okay. So that will give me NP as 720. So now in this case, you see that your voltage in the secondary coil, you're going to drop it. It's a step down transformer. So number of turns also should be down to the secondary coil, that is 30, and starting primary coil, I have 720 turns. Okay. And now we're going to move on to the B. B is the current in the primary coil we need to find. Again, the current relation will be different because you know that the voltage ratio is equal to the NP over NS, same ratio, but current ratio will be opposite. That means NP over NS will be equal to current of the secondary coil divided by current of primary coil. So I have those information in your lecture part. Make sure that you watch it, how you get these relations. Okay. So now in this case, I know that I will be able to calculate IP easily. That will be IS times, sorry, it's my IS times NS and divide by NP, right? So that will be 700 times 10 to the negative 3, and in S is 30, and in P we found at 720. Okay, so now I can calculate the current of the primary coil. That will be equal to point. Okay, so let's write from milliamps. So I have 29 milliamps. See, that means I can write it as 29 times 10 to the negative 3 amps. That is B. And C, I'm going to do it here. C is asking the power transferred. So now power on the, we know that power of the primary coil, we can write voltage of the primary coil and current on the primary coil. And also this will be equal to the voltage of the secondary coil and also current of the secondary coil. Oops, yes. Right. So because of that, power for the primary coil and the secondary coil will be the same. You can calculate by using Vp and Ip or Vs and Is. Okay. So now this one I can calculate. I got 3.5 watts. Okay, let's move into the last question. So last question, I include about little bit about polarization into this lecture part because it is actually part of electromagnetic waves, but I included it in here because we have a lot of things to discuss in next chapter, next lecture. Because of that, I think it is better to do it in here since we have the knowledge of electromagnetic waves already. Right. So now polarized and unpolarized light. So we use usually letters, the symbols. This is represent the unpolarized, that means all direction light. And this symbol represent the polarized light, right, to one direction. So now there are intensity that we can calculate how much it will absorb by the molecules embedded in the polarization sheet and how much it's going to get outside to the polarization sheet. That's basically intensity. So we talk about the intensity by using unpolarized light. If you have unpolarized light, this is unpolarized. If intensity is I naught, If you keep the sheet, this is axis of the polarization. It doesn't matter which direction you keep it. You can rotate, keep it horizontal with the angle. It doesn't matter. It will definitely pass the light of the intensity. That intensity will be equal to I naught over 2. That is the one rule, right? And the second important rule is, if you send the polarization light, we'll say this one is now I naught. If you send this light through the polarization sheet, now angles matter. So we'll say this is tilted a little bit. Your axis will be sitting like this, and this will be your incident light. And if you know this angle, then we will be able to see your light will be transferred through these molecule holes, that embedded holes. But this intensity now equal to I naught over 2 times angle between your incoming light and the polarization axis, give you the intensity. So that's the two rules that we need to follow. Okay, so that's the concept part for that. Now let's move into this question. So now you have unpolarized light in the beginning. Unpolarized light, you're going to draw it. Intensity, call it as S. You can use any letters, any symbols for that. S is incident on the series of polarization sheets. The first sheet has its transmission axis oriented at 0 degrees. That means your transmission axis, you're going to keep like this, right? So there is nothing important in here. It's oriented at 0 degrees. So when you keep it with the 0 degrees, you can keep it horizontally or vertically. It doesn't matter. 0 degrees measured with respect to your line axis and the incoming light, right? So now as soon as you know that, this will transfer only this vertical light, that will be S divided by 2. That is your first polarization sheet. Now, a second polarizer has its transmission axis oriented at 45 degrees. Now you have the polarizer. You're going to keep the transmission axis in 45 degrees with the incoming light. This is 45. So now this is your second polarizer. Now you will pass the intensity in here. That will be S over 2 and cosine squared and 45 degrees. As soon as I know that cosine 45 is 1 over root 2, this is 1 over root 2 and power 2, right? That will give me S over 4, right? Okay, now that is S over 4. Now I have another sheet. What is the next sheet is? Third polarizer oriented with its axis at 90 degrees. Now you're going to keep the polarizer at 90 degrees. 90 degrees means your third polarizer, you have it 90 degrees. That means you're going to keep it in this way. Okay, with respect to your initial polarized axis. So now, but what you need to understand, this angle now 45 degrees, right? Because of that intensity you pass definitely will go this way, but this intensity will be your incident intensity divided by 2 and times cosine squared 45, right? So now this will be S over 8, cosine squared 45 is 1 over 2, that will be S over 16. Okay. Okay, so now what is the question is, determine the fraction of light intensity exists in third sheet with and without second sheet. Okay, so now let's see with, because we have done all everything now. With second sheet, with second sheet, intensity will be S over 16. Okay, and now without second sheet, without second sheet, what will happen? If you don't have the second sheet, so that means if I cancel out this everything in here, what you have is you have, let's redraw it. The second sheet, without second sheet, you have this S over 2 incoming. There is no second sheet, but you're going to go to the third sheet directly here. So now angle between your incoming and the your sheet will be 90 degrees. So now what you get in here, S over 2 cosine is squared 90 degrees. This part is now 0. Because of that, your intensity will be here 0. Okay, so that's it for this worksheet.